Jnanam Paramam Dheyam. Knowledge is supreme.
So, now here also the immediate corollary to this is, if I have a prime ideal P in any ring, a Noetherian, then height of P is finite, because this P will be generated by some element, and then we apply the Krull's generalized theorem to this P. So, height P will be less equal to the number of generators. So, actually height of P will be less equal to mu of P, that is we have noted last time now. So, therefore, in particular dimension of a local ring is finite. So, in particular dimension of a local ring, which is height of P, no, in general actually dimension of a local ring, A local, this is finite. See, dimension theorem guaranteed this, and because it is a degree of the Hilbert-Samuel polynomial, etc. So, okay. If you notice, I wanted to write a proof in the exercises that remember in the normalization lemma we proved that a finite type algebra over a field is integral over polynomial algebra, and that the number of variables is therefore the dimension, right. So, for a finite type algebra, I wanted to prove that the polynomial, the sum, I wanted to prove that I wanted to have analog of the Hilbert-Samuel polynomial for finite type algebra. So, A is finite type over a field okay, and we somehow know, not by using dimension theorem, we somehow know that the dimension of this finite type algebra A equal to the number of variables which appear in the Noether's normalization lemma. So, this, so D which appears in NNL. But this I wanted to also show it by using the proof similar to Hilbert-Samuel polynomial, and I wanted to cook up some polynomial function with rational coefficients whose degree is related to this D or D minus 1 in, so that will match with the dimension theorem, right. So, but you remember that to define that polynomial I have to have a graded module and graded rings and so on. So, finite type algebra is just A is just K x1 to xn modulo some ideal, and this ideal may not be homogeneous ideal or anything. So, what I wanted was suppose this small xi's are the images of capital Xi in this residue class ring, then from such a I want to define a polynomial function. I want to define some numerical function and check that numerical function is a polynomial function, and that D I wanted to check this D, right. So, first of all there are too many hurdles. Number one hurdle is these generators may depend that polynomial function which I will define will depend on the generating set. So, somebody may have different algebra generators of this, and then the polynomial corresponding to that, as if you have read that it is not unique, the polynomial is not unique, but what is unique is the degree is unique. So, that is what I wanted to do it more carefully, and maybe on the way your difficulty will disappear. Okay. So, the polynomial what I wanted to define here was, so this also I will do it precisely today in the exercises. So, that will get tied up with many other things. Okay. So, another thing now today I just wanted to mention that if I have a ring homomorphism from A to B, then we have a map from spec B to spec A, namely any prime ideal Q in B, you contract it to A. Right, and so contraction of a prime ideal is prime ideal, but this will not map in general maximal ideals to maximal ideals, because contraction of a maximal ideal need not be maximal ideal, but that we know it for if you assume further A and B were finite type algebras, but in general we may not have that. So, and also I guess you know what is the topology on spectrum, right. So, so consider this now as a topological spaces with Zariski topologies. So, this is a topological space, this is a topological space, then I want to check that this map is actually continuous. So, then this map is continuous in Zariski topology. Do you already know that, or shall I check it? Okay. So, how do you check some map is continuous? Inverse image of an open set is open, or inverse image of a closed set is closed, and so on. So, that means we want to check. So, let us give some names to this. So, this is phi, then usually this is called phi star. So, and a closed set we know, closed set is typically of this form V of A, where A is an ideal in A. So, when I want to pull it back under this, so phi star inverse of this, and what will it be? So, you need to prove it is closed set, right. So, V of somebody, but that should be an ideal. So, who is the likely candidate? A, you take this ideal A and extend it to B. So, A times B. Either check this is easy to check, because you can take one element here and check it is here, and the other way also, because if somebody contains here, that means somebody contains Q ideal, prime ideal Q, if it contains A times B, then contraction of Q will contain definitely A. So, that means contraction will belong to this image. So, that means phi star of Q will belong to V A, and conversely also similar. Or I wanted to also remind you that to check some map is continuous, you can do little bit economically better, because you only have to check that the basic open sets are the inverse image of the basic open sets are again open, and basic open set, you know what is the basis of the topology? So, this word is not like what we use in linear algebra or algebra, but this basis means similar to that. That means any open set, or you think of it as a collection which is a collection of open sets, so that intersection of any two members of that collection will contain somebody like that, then it is called a basis. Or equivalently, any open set will be union of this collection. So, there is a nice basis for Zariski topology. So, what is the basis, do you know? So, basis for a Zariski topology. On a spectrum of A. So, that is, you take any f in A and look at d of f. This is by definition, you need open. So, take the complement of V of f. V of f is same as V of ideal generated by f. So, this is definitely open, and any open set will definitely contain this, because any open set is of the form complement of V of A, but A will contain some element, and that, so it is clear that this is a basis. And so it is, see, this is also directly you can define, this is all those prime ideals P in A such that F is not in P. So, one problem normally at the beginners level, one normally come across is the notation, and one remedy for that notation is, so when you want to do algebra, think of prime ideals. So, think of spec, the same thing. You algebra, I will use the notation P, right, because that will also, and when you want to do topology, geometry, etc., instead of this you write X, topological space, and instead of this you write small x, a point, and then this P and this X, there is a one-to-one correspondence, right. The same x you are denoting in this notation by P, and the same P in this notation you are denoting by X. So, this you should also keep in mind, this is Px, right. Now, what happens? Now, we have this ring A, we have A mod Px. Now, this is integral domain, so it has a quotient field. So, that quotient field in algebra notation is this, right. That I want to denote by, there is no field anywhere, this is a field. So, that field I want to denote by kappa x, it only depends on x. And so, when you think of a topological space and x, this is a field attached to that point, it is called a residue field at that point, and there is a natural map here, there is a natural inclusion here, right. Now, let us check where do f go here. If I have an element f here, where does it go? It goes to f bar, the residue class of f in A by Px. So, that is f bar, and this f bar goes, this is natural inclusion. So, it will keep going to f bar. This f bar I want to denote by f of x. This is just a notation, but now see the magic. So, when will this f belong to Px? So, let us write down that when f belong to P, P means Px, if and only if this is 0, if and only if that is 0. So, that means f of x is 0. So, this is, you get a feeling like evaluation at a point and 0 of f and so on. So, this is very handy especially when you want to check this is a topology, right. Suppose you want to check, let us check one equality already, so that you will feel ease at this. So, tell me one property that V of A intersection V of B is equal to V of A plus B. And V of AB equal to V of A union V of B. So, let us check this for second first, for example. So, that means I want to check that, let us take x in x. Now, I want to check that x belong here if and only if it belongs here. So, we will prove that x belong to LHS if and only if x belong to RHS. So, x belong here means what? That means the prime ideal contains A times B. That means if you take all products, that will vanish at that x. So, this is f times g at x is 0 for all f and g in, for all f in A and g in B. But you see this evaluation map, this is a ring homomorphism. So, whether I product and evaluate or evaluate and product, that is the same operation. So, this is same as f x times g x, but f x and g x are elements in the field. So, that will imply f x is 0 or g x is 0. And therefore, so this is usually how, this is the quickest way to prove it. Okay, and this notation is due to Grothendieck. Okay, so this means we have here category of rings. That, do you know what is the category? So, that means it is a collection of objects. Category means it is a collection of objects. The objects could be sets, groups, rings, vector spaces, algebras over a fixed ring, or topological spaces, or differentiable manifolds, or any subject you are studying. Those are the objects, and the morphisms are the corresponding homomorphisms. Like if you are studying groups, then group homomorphisms; if you are studying ring, then ring homomorphisms; if you are studying differentiable manifold, then the differentiable maps; if you are studying Lie group, then the Lie group homomorphisms, and so on. So, that together form a category if it satisfy certain rules like respecting composition and so on, right. So, category of rings on one side, actually commutative rings we should say, and category of topological spaces. And we have a functor. Functor means each object is associated to an object in such a way that if there is a morphism here, there is a morphism there, and so on. So, that data is a functor, and the functor is called equivalence if it is like there is the other way direction also functor, and so that each composition is identity and so on. So, they are suitable definition, but that is just language, and here we have a functor, namely spec. Given a ring, we have attached a topological space to that. And what one wants to do is, one wants to study, one wants to get information about the rings by using the topology information, and one would like to actually come back also. That means this is a natural equivalence. So, that means from this given topological space, one wants to recover your ring also, and this interplay is precisely the what is called abstract algebraic geometry. Okay, so this actually is not quite correct, because what happens, we have to put some restrictions and put some correct definitions. For example, if you take, say, very simple example, kx mod ideal generated by x square, then what is the spectrum? Then spec of this is only one ideal, right, namely ideal generated by that small x, where small x is in the image of capital X. See, such problems will also come with the notation conflicting. So, one has to use the variable capital T and small t and so on. Anyway, so this is an Artinian ring with only one maximal ideal, and if I would have taken field, then also there is only one point, namely the 0 ideal. And the topology is clear, this is a discrete topology. So, how are you going to recover, or you recover this or this? So, there is, it is not quite correct, you will have to assume the ring is reduced, then whether you can recover or not. So, it is all this. So, whenever I have more and more time, I will keep adding these comments with respect to the Zariski topology and the category of rings.